please.
Yeah.
Yes, now we can start. So
yeah, before going to start our session, let me introduce you to the students. Yeah. So shall we start?
yes, sure, please. Yeah.
Good morning to everyone. So I welcome you all to the lecture series in nonlinear dynamics. And it's my pleasure to introduce you today's morning speaker, Professor Sariga Chalan from IIT Indore. I want to introduce today's speaker for the MSc students because most of you may not aware Professor Sariga Chalan's background. So she got her PhD from Physical Research Laboratory, Ahmedabad, and then she continued her postdoc in two institutes in Germany. One is Max Planck Institute for Mathematics and Sciences, and another one is Max Planck Institute for Physics of Complex Systems. Then she worked as a senior research scientist in National University of Singapore for some time, and she joined as a faculty in IIT Indore in 2013, and she is working in IIT Indore to present date. And she is acting as an editorial board member in few journals, and she is chief editor in the Journal of Computational Sciences. And she is running several projects, research fund projects, including a couple of internationally sponsored research projects. And as far as other things are concerned, Professor Sariga Chalan is one of the very active persons in complex systems group in India. And upon visiting her webpage, I understood that several master's students from all over India did summer internship under her supervision. Several students completed PhD under her guidance, and many of them are in several European countries. For example, Sweden, Israel, Denmark, Norway, USA. I pointed out few countries where her students working now, and she is monitoring the works of several PhD students right now. Okay, despite her heavy teaching, because in IIT, you have a very heavy teaching. Besides teaching, she is monitoring several PhD works. It is understood that Professor Sariga is a very busy person, and without wasting much further time, let us move on to her to hear her talk. Professor Sariga, over to you.
Thank you, Professor Senthilvalan, for very nice introduction. And now let me share my screen with which I start my talk. So all of you can hear me, and let me put in the slide mode, play from start. Okay. So all of you can see my screen, because now I cannot see you all actually. This is the problem if I do full screen. So can you all hear me and see? So please feel free. One thing is that please feel free to ask question, interrupt me in the middle, okay? And in case if you don't want to speak, you can write your questions in the chat box, and I would try to share those concerns. So please keep on interrupting me. There's no problem, because as Professor Senthilvalan has said, that this talk is mostly for the master students or the budding students. And my intention today is two. First intention is that I should share with you the excitement of this new type of research, which I have been involved in last few years. And second thing is that to give you some background literature, so that if you are interested, you can start working in this field after my talk. So this is my two intention, and I would try to stick at very basic levels. In addition to give the latest results also. So today I am going to tell you a very exciting area which I have been working from last 3-4 years, and that is explosive synchronization. And so explosive synchronization is one keyword for my talk. Another one is multi-layer networks, because explosive synchronization, I will introduce what is explosive synchronization, but what I am fascinated about or interested in is explosive synchronization in multi-layer networks, and how to achieve it, that is interlayer adaptation. So there's three things: explosive synchronization, multi-layer networks, and interlayer adaptation. and I will introduce all these things one by one. And this particular research area, I have been involved in last 3-4 years with my PhD student who is now postdoctorate in Israel, Aradhana, with whom I started with. And the full peak of this research was achieved with one of my postdoctorate, Ajaydeep, who is in my lab, and Anil, who was also PhD student, and he has just submitted his PhD on explosive synchronization in multi-layer networks. With this, let me now start immediately with the Kuramoto oscillator, which is the model which I am going to use. So I understand the background which of audience here is at least basic mathematics and physics. So let me introduce my model, because this is my favorite model, which is very popular Kuramoto oscillators model. And last 30 years, like this model was introduced by Kuramoto himself in 1984. And after that, like so many papers, so many work have been done on this humble, simple Kuramoto oscillator, which let me now introduce. So this Kuramoto oscillator is simple phase oscillator, one-dimensional. You can see d theta I by dt. It means phase theta of ith oscillator is changing with time with intrinsic frequency omega. So it's just now, please ignore this coupling term, ignore this red circle. So now you can see that
excuse me, madam, your slide is not moving.
My slide is not moving.
Yes.
I am in the which slide you are seeing? Kuramoto oscillator slide?
No. First, we are seeing only your that.
Okay, so let me stop sharing again and let me again share, because window and share. Can you see my slides now?
No.
Again, you cannot see Kuramoto oscillator slide.
Yes, now we are seeing.
Now you can see, yes. So now you can see this very simple Kuramoto oscillator where theta, phase of ith oscillator, is changing with time with intrinsic frequency omega I. So here the right hand side, if you can see the circle. So with time, oscillator will keep on moving in this 0 to 2 pi circle with constant velocity decided by omega I. Okay. Now, as soon as you introduce this coupling is K by N is the coupling strength, N is the number of oscillator, for example. And here you can see this sinusoidal coupling. As you introduce the sinusoidal coupling, several emerging behavior arise, and I will just concentrate and focus on one emerging behavior, which is synchronization. And synchronization here is defined exactly like in this manner, that if theta I is equal to theta j for all time t greater than t0, then I say this all the oscillators are synchronized. And if they are not synchronized and they are homogeneously distributed between the circle 0 to 2 pi. And there's the order parameter, which is complex order parameter r e to power iota psi, where psi is the mean phase of the oscillator. And it is given by 1 upon n summation over e to power iota theta j is running from 1 to n. And now here you can see with very simple mathematics that if theta I is equal to theta j for all the oscillator, then this order parameter r, that will be 1, okay? And if theta I are distributed between 0 to 2 pi, this summation will give you almost 0. So 0 means incoherence, oscillators are distributed into an uniform circle, and r is equal to 1 means coherence, all the oscillators are synchronized. Now let us please pay your attention to this picture, which is in the right hand side. Now lambda is the coupling strength, which is K by N. So in the beginning, when coupling strength is 0, oscillators are not synchronized and R remains 0. And as coupling strength is increasing, you can see smoothly oscillators are coming closer and closer, getting synchronized, and then slowly R is becoming 1. So as coupling strength is increasing, your order parameter will keep on becoming 1. And there's certain condition which has to be followed, which I will try to introduce also, but I would not try to give so much mathematics to avoid to drift the essence of my exciting research. So here, those oscillator which is satisfying this kind of conditions. Analytically, the gist is that analytically we know that how this entire Kuramoto oscillators working theory, and we know the entire theory of working functional of that, how this Kuramoto oscillators, they show the second order transition to synchronization. Okay. And now I will show you one video in order to motivate you that how this kind of things are achieved, just to give you a glimpse of. So here now I have suppose this many Kuramoto oscillators. So green dots, they represent Kuramoto oscillators, phase oscillators, okay. And initially they are distributed in the circle, you can see. And this red line, that indicates here the order parameter. So if the distance between these red dots are larger, it means the order parameter is large. So this length of this object, that tells me the order parameter, and this is the phase. Now what I'm doing, now I'm starting the simulation, and in the simulation I will keep on increasing the coupling strength. Okay, so let's see how does it work. So can you see my, yes, you can see my slides. So just one second now. This is not working. I had a very nice movie for you all, and I'm so, this movie is not working here. Why? That's really bad, because I wanted to show you a movie. So maybe if time permits, later on I will show you a movie again, because I have to go out from the slide. But the thing is that as you keep on increasing the coupling strength, they will keep on getting the synchronization. Okay. And as this chronological order, which I wanted to say, that Kuramoto introduced this oscillator in 1984, and very nice review article, which I personally liked, and it's written very nicely by Strogatz and appeared in FISCA D 2000. And the name is From Kuramoto to Crawford. So I would suggest to all master students to go through and read this article in order to get that mathematics of Kuramoto oscillator, as well as that what new fascinating phenomena which you can achieve. And since its birth in 1984, this Kuramoto oscillator has kept on fascinating the physicist and mathematician alike. And recent advancement in the Kuramoto oscillator is chimera, which is the coexistence of coherent and incoherent dynamics, which has drawn a lot of attention from nonlinear dynamics community. And explosive synchronization, which my talk today would be focused upon. So I am not going to talk about chimera. I will only concentrate on explosive synchronization achieved in Kuramoto oscillator in multilayer network. Okay, and this explosive synchronization was introduced or witnessed or came into highlight by this paper by Gardner et al. In 2011. So let me now focus on the explosive synchronization in Kuramoto oscillator. So now there's a question that lambda denotes. So let me just read how I can see the questions. Just one second. It's very difficult. Zoom, actually, I am much more familiar on show caption. How I can read the question, because I can see there is one question which is there, but I cannot read the question. So maybe if someone can read.
Shall I read, madam?
Yeah, please, because I don't know where is chat. Madam, chatting, I cannot see.
Or maybe Prashant, you can unmute and ask now. Prashant?
Because okay, I'm trying to see chatting, but I cannot.
In the second slide, actually lambda, what it denotes, ma'am?
Lambda is the coupling strength. So it is showing that how strongly the oscillators are interacting with each other, and that's it. Okay.
Okay, and R is, ma'am?
R is the order parameter. Okay, order. Maybe you keep on writing, because I will try to address the question in 15 minutes interval, and then one can read. Okay. R, I have just explained. R is the order parameter. Okay.
Okay, thanks.
Okay. So now one can see that I am just focusing upon the explosive synchronization. Okay, so let me again maybe try to explain again. The R is the order parameter, which is 1 if all the oscillators are synchronized, and 0 if oscillators are not synchronized. Okay, and lambda is the coupling strength. With that, I will be only focusing on the explosive synchronization. Explosive synchronization means first order transition to synchronization. And then I will focus on multi-layer networks. And again, there is one nice review article in multi-layer network appeared in 2019, which gives you that why multi-layer framework is important. But I will also introduce that what is the multi-layer framework and explosive synchronization one by one. So now my entire focus would be explosive synchronization in multi-layer network, which is relatively new field of research. Now, as I said, second order synchronization means that if you are slowly increasing lambda, okay, then your order parameter will keep on increasing slowly and it will become 1. Okay, so all oscillators are keep on getting synchronized. R is, again, let me remind you, R is the measure for the synchronization. Now, first order transition to synchronization. Now here, please pay your attention that as lambda is increasing, again the coupling strength, as coupling strength is increasing, you can see R is 0. It means the oscillators are incoherent, and then there's sudden jump. You can see there's a sudden jump in the value of R. Small increment in lambda, so that you see in the magnetism. So you have a phase transition, first order phase transition. So it becomes 1. And you keep on decreasing R, you can see that there's hysteresis. It adopts a different path. Okay, so first order transition accompanied with the hysteresis, that is a first order transition, that is known as explosive synchronization. And how explosive synchronization is achieved? So because if you have all-to-all coupling, you have only second order transition to synchronization. So there are two parameters which are very important. One is the network architecture. So it's not everyone is connected with everyone. And I suggest please write down your questions in the chat box, because I'm seeing that breaks the harmony if I keep on addressing all the questions. But please keep on writing down the questions in the chat box, and I will see any relevant question which is not drifting too much from my talk, I will address now. Otherwise, I'll take all the questions to the end of the talk. Okay. So please keep on writing down. I don't want you to discourage to write down the questions in the chat box. So now you can see that there's AIJ, which is the network architecture. This is the one important parameter which can govern whether I am getting the second order transition to synchronization or first order transition to synchronization. And second parameter is the intrinsic frequency and the relation between the intrinsic frequency and this the network architecture. So these two parameters govern whether I am getting the second order transition to synchronization or the first order transition to synchronization. Now, again, I have this movie, and let me see if this is again not working. And I am very much that this is first time it's not working. I don't know why it is not working, because I had very nice movie to show you that whether, so can I end, I don't know, because I think maybe because of Chrome, it's not working. Okay, so I'm very sorry that this movie is not working, where I have tried to show that how second order transition to synchronization happens and how first order transition to synchronization happens. Can I take just a small break and try to see if I can show you this movie into another browser, which is, I don't know, let me see, this is not working. No, I don't see this movie part here. So yeah, this is not working. So slideshow. Can you see my screen?
No.
Still?
No.
You cannot see my screen. So I don't know why it is not working. Just give me a few seconds. Let me work it out. Maybe I open. Just few seconds, because this movie was very important, very nice, and that's why I want to. So I'm opening another slide where I thought that I can show you, and let me see if it is. Yes, it is working here. So I'm sharing another screen, and I will try to see whether, okay, so a window, and here, yes. So here it is working. So slideshow from current slide. So can you see my slide?
Yes.
Okay, and now I'm showing you for second order transition to synchronization. So this green dots, they represent the oscillators, okay, and this red dots, that is the order parameter. So now you can see as I am increasing the coupling strength, oscillators are coming closer and closer.
Can you please move on to slides more? Your slides are not moving.
Oh, slides are not moving. So I think this is a problem with Chrome. So I am not trying now to. So let me not try to show now this one. Okay. I'm not showing that. I'm trying to proceed without now showing that. Okay, so without any further ado now, so let me now share the same thing. Okay, so I am not showing the movie. Maybe I'll share it later with all of you. So explosive synchronization means sudden jump, and second order transition to synchronization means R is increasing slowly. I wanted to show the same thing using the simulation, that suddenly you will see that R will jump. Okay, and why we are interested in first order transition to synchronization or explosive synchronization? Because explosive synchronization has been shown to have a lot of harmful effects in physical and biological systems. And here I have given few examples, that chronic pain in brain that is attributed to be caused because of the sudden jump in the synchronous activity in the brain. Similarly, cascading failure of the power grid, that also the fine tuning of something, and suddenly there is a cascading failure of the power grid. So that is also known to be attributed to the explosive synchronization. brain disorders such as seizure, Parkinson disease, there is a increasingly debate whether those are because of the explosive synchronization or not. So these are the area which have drawn a lot of attention for nonlinear dynamics people to work on this phenomena of explosive synchronization. Okay, so there are enough real world system which show this kind of sudden jump in their synchronous activity, and that's why we are interested to understand that what leads this kind of sudden jump in real world systems. So we want to understand the mechanism behind observation of explosive synchronization in real world system, that sudden change in coupling strain leads to this jump and why it happens. Okay, and there has been a lot of work in last 7-8 years from 2011, last 10 years, to understand the root cause of explosive synchronization. And here I am not going to explain the entire thing, but I want to say all this work so far has concentrated on only one layer networks. Now I will show what is the multi-layer network. That is now the next few slides. I will try to explain that what is a multi-layer networks, but all this work so far have focused on only one layer networks. Okay. Whereas now, let me now explain. Let me try to give you.
Madam, again, excuse me, madam. Again, the slides are not moving.
Yeah. I don't know what is happening because in general it works so fine. So stop sharing again. Again, I have to keep on doing the same process. PowerPoint slide, interlayer adaptation. So can you see now slides? My slides?
No. Yes, no.
Yes, it has come actually. It takes us some time. So I was showing that after this slide, I was showing that there's a lot of real world system where there has been harmful effect of physical and of explosive synchronization, and these are here. And with that, let me come to the next slide, that there has been a lot of work which has been done on explosive synchronization, but all those work on only one layer networks. Okay, whereas my work is on the multi-layer networks. And let me try to explain what is multi-layer networks. So by definition, multi-layer network is a set of n nodes interacting in m layers, each reflecting a distinct type of interaction. That is the mathematical definition of multi-layer networks. And I can give you a few examples of multi-layer networks in real-world system. For example, a transport system of a country can have a different modes of transportation. For example, same cities can be connected through airport. So flight network can form one layer, railway network can form another layer, and the bus transport can form another layer. So you have the same system, but they have a different layers. Okay, and you know that activities of one layer affects the activities of another layer. For example, if there is a strike, railway strike, you can find that there is a sudden change in the fare of the airport for the flight connection. So activities and a structural pattern of one layer that affects the functional performance of another layer, and that is the gist of multi-layer networks. And there are some examples of multi-layer networks here. So now slides are visible. Okay, so so this is a Madrid multi-layer transportation system where different layers are, one layer is tram, one layer is metro, and one layer is bus. Okay, so you have this real world data. Now you have social networks where you have Google, Twitter, MySpace. So people are here are the nodes. Okay, and if they are following each other, for example, then they are connected. So into Twitter, if you are following some other person, it means both of you are connected. Simply in Google, if you are following each other, or if you are searching their web page, or Facebook, so one layer can be Facebook. So you can see same set of the people, depending upon which layer they are interacting, they can form different types of layers in the same system. Okay, so information flow in one layer would greatly affected how they are connected in the another layer. Okay, in the brain, you may have different frequency bands in the brain, and you can have functional and physical structural layer, and both of them affect each other. So some functional performance of one layer affects the structural performance of another layer. So activities of nodes in one layer may evolve its impact on the functional performance of another layer. And that's why this multi-layer framework has got a lot of boost in last 5-6 years, because people have realized that ignoring impact of multiplexity may result in the wrong prediction of the behavior of individual layer. Like the example which I have just quoted, it's written here, a strike of the bus service may result in overloading the rail and air traffic routes. With this, now we can take this kind of things to our advantage. And one thing is that we can control properties of entire multi-layer networks by tuning properties of only one layer. So as we know that property of one layer gets affected by another layer, it means we can control also the property of one layer by tuning the properties of another layer. With this, now let me come to some mathematics. That adjacency matrix of a graph, if you are aware of that Aij, A is the adjacency matrix of a graph, and Aij is equal to 1 if I and j is connected, and Aij is equal to 0 if I and j is not connected. So this is the adjacency matrix of any graph. For multi-layer networks, let's see now how adjacency matrix you can write down for multi-layer networks. So layer 1, adjacency matrix of layer 1, this is Aij. So Aij is equal to 0 if I and j is not connected, and 1 if they are connected. Layer 2, you have this. Now let's come to layer 3. So you have first layer, which is here, layer 2 here, okay? So let me again try to show. So layer 1, layer 2, and then now we are having the multiplexing, which is coming into the diagonal element. So diagonal element here is 1, which is the identity matrix, which accounts for, so diagonal block accounts for multiplexing of first layer on the second layer, and which is the mathematically depicted here. So we have A1, which is the adjacency matrix of first layer, A2, adjacency matrix of second layer. Dx is the multiplexing strength, so how strongly the activities of first layer is affecting the activities of second layer. And I is the identity matrix accounting for one-to-one interaction between the two layers. And now let me now change my this Kuramoto model, which was single layer networks, to the multiplex network model. So now this left hand side, again, I have the phase evolution of the oscillator in the first layer. So now you can see this subscript that accounts for whether I am talking about the first layer or the second layer. I is the ith oscillator, and 1 here indicates that whether my oscillator is in the first layer or my oscillators are in the second layer, okay? Omega I is the intrinsic frequency of the ith oscillator in the first layer, plus lambda 1, that how the ith oscillator is interacting with all other oscillator in the same layer. So first and second term in the right hand side, the same exactly as I had shown previously in my slide for the Kuramoto oscillator. Only new term here, which is the multiplexing term, which is the DII, where DII is connection between the ith oscillator of the first layer and ith oscillator of the second layer, and again with the sinusoidal coupling. So sine theta 2 here represents the second layer and 1 here represents the first layer. So how ith oscillator of second layer is interacting with the ith oscillator of the first layer, and that is the third term, and which is the new term accounting for this multiplexing. So now we have oscillator for the first layer. First equation is the oscillator for first layer, and second equation is for the oscillator for the second layer. Now my order parameter, now you can see this multiplexing strength is given by DII. And again, my order parameter here would be for R1 for the first layer and R2 for the second layer. So my order parameter remains same as I had given in my second slide, but now I have indices R1 and R2. So R1, all the oscillator in the first layer will come, and R2 means all the oscillator in the second layer. So again, R1 would be 0 if my oscillators are not synchronized, it 1 if the oscillators are synchronized, okay? So now if I take this kind of multiplex network model, again, I get the second order synchronization. If I don't do anything from outside, I will show that how one can induce the first order or exclusive synchronization in the same model. So if I take A1, A2, and omega 1, omega 2, like omega 1, omega 2 uniformly distributed, A1, A2 simple Eros-Renyi random network, then this kind of model, multi-layer model, will give me the second order transition to synchronization, which is the smooth one. Now I'm going to provide you the strategy to which that same system, I won't do anything in the A1, I won't do anything in the A2, I will only play with this multiplexing. This is the only new thing which I am trying to focus upon. I will play with multiplexing, and I will show that how this entire system, just by remaining A1, A2, everything same, by playing this multiplexing thing, can lead to the very different route to synchronization, and which is the first order transition to synchronization. So now this was a slide which is working actually very nicely. So adaptation through Hebbian learning. So now this one, I will evolve this multiplexing strength using this Hebbian learning thing. Okay. And now what is Hebbian learning rule? So Hebbian learning rule is motivated from, is given for the brain. Okay. And it says that if two neurons, if they fire together, coupling strength between them, that will increase a lot. And that Hebbian gave this theory in 1949. And later on, it was actually demonstrated experimentally that this rule works. So those neurons which fire simultaneously, coupling strength between them, that also increases. And this kind of Hebbian learning gave birth to this entire business of brain plasticity and machine learning algorithms. And then I will show that how using this Hebbian learning rule, the same network which was incapable of showing explosive synchronization starts giving you the explosive synchronization. So gist of Hebbian learning is that cells that fire together, they wire together. So those who have synchronous activity, a pair of neurons, if they have synchronous activity, the coupling strength between them will also increase. So connection between synchronous units get stronger. And now let me tell, now same model. So first I had the single layer network model, which I showed in the second slide. Now I introduced this DII term, which accounts for multiplexing. Okay. And now I am showing that how I am changing DII. I am not changing anything here in the second term or the third term. And why I am emphasizing on this part, because all the previous researchers have shown that one can change omega 1 and A1 and relation between them in order to get explosive synchronization. And here I am saying that I am not neither changing omega 1, neither I am changing A1, nor lambda 1. I am not doing anything in the intra-layer part. I am only changing DII. And just by changing DII, I can get the explosive synchronization in the network, which was not showing that. So Hebbian rule adaptive. So now let me introduce how DII is changing. So here now you see DII is evolving with time. So DII dot, this is the Hebbian learning rule. Hebbian learning rule that if theta 2 is coming closer to theta 1, you can see if this term becomes 0, this is highest. Okay. So as my activities of mirror nodes, they are coming closer, my DII will keep on getting higher and higher. And minus DII term in order to give the normalization so that it doesn't exceed to a certain value. Alpha is the learning amplification rate and epsilon is the learning rate. So this is very standard Hebbian learning rule, which people know, but as far as I understand, first time we have employed is in the interlayer connection. Okay. And I want to emphasize on one paper by Scholz group, where they have done the same scheme, like same model they have taken, but they have given this adaptation into intralayer. Okay. So they have, instead of DII evolving, they have evolved lambda 1 with the Hebbian learning rule. And again, I want to emphasize that we have not done any changes here and here, and we are evolving interlayer coupling, whereas other papers, including this very nice paper by Scholl, they have evolved this intralayer adaptation, and we are doing this interlayer adaptation. This is the one basic difference. And now this is the results. First, I will show a few results, and then I will try to give the theoretical framework for that results. Okay. So now you can see this is the multi-layer networks. When epsilon is equal to 0, it means there was no learning. You can see as lambda is increasing, R1 and R2, which is the order parameter of the first and second layer, that shows a smooth transition to synchronization. So here it is 0 to 1, a smooth transition to synchronization. As soon as I make epsilon non-zero, it means I introduce this Hebbian learning in DII. So in this case, DII remains constant, where in this case, bottom case, DII is increasing with, is changing as per as the Hebbian learning rule. So one can see the explosive transition. It means in the positive direction, you can see jump, and the reverse direction, you can see this is the hysteresis. So just by having this Hebbian learning rule, we can get explosive synchronization. With this, let me take up some questions if they are written. How I can see the chat box? Let me not see chat box. If there are certain questions, can sudden transition? Okay, so there was a question that lambda denotes synchronization population, so that I had already addressed. That shows the coupling strength. And there's another question by Sudarshan Silva Kumari. Can sudden transition without hysteresis be called? Actually, this is a very good question, actually, Salva Kumari. And we had many times we discussed on this thing that without hysteresis, can we call it explosive synchronization or not? And for that, I have to give some mathematics that explosive synchronization means what? You have two states which are stable, correct? You have a state which is incoherent and the coherent state, okay? And as far as I can say that we have to have hysteresis in order to call it first order jump, because you have bistability. And that is, so answer to your question is that in general, we don't refer it explosive synchronization if there is no hysteresis. So hysteresis, you will always get in general if you get explosive synchronization. But for hysteresis, one thing you have to remember that lambda has to decrease adiabatically. So very small decrease in lambda, which you have to do, and then you will get hysteresis. So you cannot, in general, we don't refer first order transition without hysteresis. So answer to this question to this. Now, another question is that by changing lambda, is it possible to get intra-layer coupling? Okay, so answer to this question. So let me again start sharing. Is there any other questions? I will answer this question, Prashant, once I start sharing the slide. Any other question which is there?
Yeah.
So I can.
Yeah.
Yes, just 1 second. I can start sharing the slide and answer the question also. Okay, so just 1 second. You're presenting your screen. Okay. So can we extend this scheme to other limit cycle oscillator? Okay, so let me now try to address these questions one by one. So first question is by Prashant, that by changing lambda, is it to get intra-layer coupling? So the thing is that whenever I am saying that we get this explosive synchronization, you can always see the x-axis is lambda. So DII is changing with time, getting settled down. But whenever we are talking about explosive synchronization, that is against lambda, that by changing this intra-layer coupling. So always I am changing intra-layer coupling. With the intra-layer coupling, as you are changing, how there is a sudden jump, okay? So that is answer to your question. And the second question, which was there by another person, Gayatri, that can we extend this scheme to other limit cycle oscillators? So as I understand this question, that whether it is possible to get explosive synchronization in other oscillators apart from Kuramoto oscillators, so answer to this question is yes. That people have shown even the maps, logistic maps also, I think, and Stewart-Landau oscillator, not Stewart-Landau oscillator, I think the Fiske-Nagmo neurons and many other oscillators, people have shown this abrupt jump in the synchronization. Kuramoto oscillator is one prototype model, but yes, answer to your question is yes, that this kind of explosive jump can be seen in the other places as well. But most of the work has concentrated on Kuramoto oscillator because of the mathematical simplicity. So it was by changing DII. So the question which now he has changed, Prashant, that whether by changing DII you are getting. So now you see DII is evolving in time and it's settling down. So start DII with some initial condition and then it evolves using this Hebbian learning rule. So DII is evolving with time. Okay, so one has to solve this 3 equations simultaneously. So 1, 2, 3 equations simultaneously. And with that, one gets this explosive synchronization. So DII is changing, is evolving with this equation. Now there's another question, why particular interaction between 2 layers? Okay, so this is very good question, Vijay. So I think you want to ask that why there is a one-to-one coupling. No, there is no need of one-to-one coupling. In fact, I will show later that even we have recently one paper which has recently published in Physical Review E as a letter, where we have shown that one-to-many layer couplings. In fact, this is the final open discussion that in multi-layer networks, how to model, whether it's a one-to-one coupling, one-to-many. So the thing is that there is no physical connection between the people in 2 layers. So this interlayer interaction that is telling you that how the activities of one layer is affecting the activities of another layer. So this DII represents that. So there is no physical meaning of one-to-one coupling. It is just a symmetric, or I say this is just one type of modeling where we are showing that how one can incorporate the dependence of one layer on another layer. So your question, answer to your question is that no, one should take, in fact, one to all, one can try. In fact, like here, like in this model, if I introduce here one summation sign and one Mij, so that takes care of your question. Instead of this identity matrix, I can substitute here one full matrix here. So one can take all those things, but then I would show that theoretical understanding of those kind of situation would be difficult, but this explosive synchronization is robust against change in this interlayer architecture. So you will still get all the results which I am showing here, that is robust against change in interlayer architecture. So instead of identity matrix, you can here put it any kind of matrices or all to all, and still you will get explosive synchronization. But the theoretical understanding is easier to get if we have one kind of very systematic kind of multiplexing. So here omega is constant. So omega is taken from, so now let me now explain this model even more carefully. So omega here can be drawn from some certain frequency distribution. In general, people take Gaussian distribution, homogeneous distribution, or Lorentzian distribution. So omega remains constant. Yes, it is not changing with time. Theta I, which is the phase of the oscillator, is changing in time, and dii, that is changing in time. Lambda 1, and we are plotting. Lambda 1 is a parameter. So we are plotting as a function of lambda 1, but intrinsic frequency, that remains constant. Alpha, epsilon, which is the learning rate, etc., that also remains constant. Now with this, I think please keep on writing down the question and let me proceed with my talk. So let me make it again full screen. Okay. So now I have shown this. Now let me just give you some few more results that how alpha is governing, which is the amplification factor. You can see we can control this nature of this first order transition by controlling alpha and epsilon. If we are not changing anything there in the interlayer,
slide is not visible, ma'am.
Slides is visible, I guess. Can you? Because I have logged into. Is it not visible to anyone?
No, it is visible. It is not moving. You have to.
It is visible. It is not moving. So which? Okay. Yes. You are right. Again, this is the problem. I don't know why this problem is happening all the time today. So now let me again share, stop presenting, share the screen. Is it coming? Can you see the screen?
No. Yeah.
Yes, it takes some time. Now this slide is visible. Now I go to this slide. The slide is changing. Now if I say play from current slide, then it becomes problem. Okay. So maybe I can do full screen. Okay, anyway. Okay, so now this is visible. So now this slide is just to show that we can control the properties of this first order transition to synchronization by governing this alpha and epsilon. So this is the only thing with this slide. Again, I can see that slides are not moving. So each time I have to go out, slideshow, and now slides are moving. Waveform. So maybe I can try one more thing. I don't go to the full screen mode. So still, is it okay if I don't go to the full screen mode? Because the full screen mode, then that's the problem which is arising. Yeah. So can you see my slides very well?
Yes, not a full screen mode.
Not is it visible? Because if it is visible, then I will go with this, because as soon as I'm putting full screen, then I have to again come out. So now these two slides I am just showing in order to tell you that one can control the properties of this first order transition to synchronization by having epsilon and alpha, and I will again show the slides if you have any question, but let me go to the theoretical framework, okay, because that's very important in order to understand why we are getting explosive synchronization. So you can see my screen, correct? So the thing is that, you know, why you get this first order transition to synchronization? Let me ask this question. So you see, as you are increasing the coupling strength, what happens that as you keep on increasing the coupling strength, oscillators which are, so all the oscillators, they try to come to the mean frequency. So suppose if we take the question of two oscillators, what will happen that the oscillator which is having the large frequency and the oscillator which is having the smaller frequency, I think someone is unmute. Please mute yourself. Please mute. Yes, thank you. So now these two oscillator, the oscillator which is having larger frequency, which try to reduce down its frequency, and the oscillator which is having a smaller frequency, that will try to increase its speed. And then finally they will come to the mean field. So because of lambda, because of this interaction, the oscillator will try to come together and form the synchronization. So that's how the synchronization occurs. And the first order transition to synchronization, explosive synchronization, means somehow oscillators are not coming towards the mean frequency. So as you keep on increasing the lambda, oscillators start forming small clusters, but they don't come to the mean frequency because of some frustration which is there in the system. And suddenly, as lambda is increased, suddenly it overcomes the frustration and you get a sudden jump. So you don't have formation of giant cluster, and that we try to understand using this mean field analysis, which is very simple. And that analysis, if you want to understand, there is this paper by Strogatz and Fiscadi 2000, that is for all-to-all coupling. And 10-12 years back, there's a review article in Physics Report, very nice review article by Alex Arena's group, and which has extended this analysis which has presented, not extension was already done, but this was reviewed in for the network architecture. But all these two papers, that is about the single layer networks, they have not talked about the multi-layer. But the mean field analysis is very simple. You write down the equation in terms of mean field. So you see the summation term in the second, that is replaced with R1, which is the order parameter. So this is the mean field analysis where you have replaced this dependence of theta j's by taking this mean field, and this is the mean phase. Psi 1 is the mean phase of the first layer oscillator, okay? And R1 is the order parameter. But still you have this third term. You can see this is the term which accounts for this interlayer connection, okay? And similarly, so now you can see you have got rid of the summation sign in the second term. And you have got rid of theta j dependence in this equation. So that is the one advantage of having this mean field analysis. And then we have locked oscillators and the drifting oscillator. What does it mean? As you keep on increasing lambda, some oscillators are coming closer and they become locked. So they start moving with the mean phase, with the mean frequency, and some oscillator which are still not locked. The oscillator which are locked, that is given by this condition, and it is very easy to get that if left hand side you put 0, which is for the locked oscillator, because they don't change their effective phase in time, you get this locked oscillator condition. And the second key step here is that you get discrete version, you take in the continuum limit. So this approach, mean field analysis approach, entire formulation work in the continuum limit. So here the discrete version of order parameter, I have just substituted here with the continuum version. So we have, instead of integration and g omega is the frequency distribution of the oscillator. So someone has asked that what is omega? So omega is the frequency distribution. So I have just gone from the discrete version to the continuum version. And then now the key is how to solve this equation. So you can see this is self-consistent equation. Left hand side also you have R, and right hand side also you have R, which has come from here. Okay. And this integration is only for those oscillators which are the locked, because it was already shown in the this Strogatz paper that the oscillator which are drifting, they don't contribute into the order parameter. Only the locked oscillator, they contribute in the order parameter. And mathematically, it can be shown actually that the oscillator which are drifting, for them, this integration becomes 0. So only the locked oscillator, they can come to contribute into this integration thing. So now you have this mean field analysis, and now the challenge here is that how to take care of this a third term, because until this was pretty easy, but this interlayer term, multiplexing term, that one has to take account of. So this is the same thing. And now let me now emphasize that analytically what one can show, as you can see that
excuse me, but the slides are not moving.
Slides are again not moving. So this slide you can see, and now I have to again insert, and then I have to go to again the second slide. So now you can see the slides, okay?
Yeah.
So now here you can see here in this slide. Yes. So I had a lot of effects which because of this problem I am not able to show, and I don't know why it is happening, but let me now stop.
Earlier you were able to do it, right? Wait.
Okay, so let me first do slideshow and then start sharing. Play from the current slide. You can see now, is it? No. Can you see my screen?
No.
Now, can you see my screen?
No.
It's coming, I guess.
It's coming, yeah.
Okay, I think
again it is not.
problem will be there, but let me, yeah, it's not a full mode. Okay. So here now what I wanted to show that you can see that by tuning alpha parameter, one can see the different values of in the forward direction and in the reverse direction, this coupling strength, and that analytically. So here what is plotted in this plot, that alpha as a function of lambda. So one can see that as alpha is changing, which is the learning rate, if you can remember, amplification factor in DII, that affects the critical coupling strength in the forward direction. And that we have tried to calculate using this mean field analysis, and where the important factor is this sigma. Sigma is nothing but this interlayer coupling term, and that we have to do some small, we have to take one assumption here, which we have taken from numerics, that sigma that is becoming, so theta 2i, so alpha by 2 sine 2 of theta. So theta 2i, that is nothing but the minus of theta 1i. So that we have taken from numerics. G omega, which is the frequency distribution, we have taken homogeneous frequency distribution. And after having this thing, we have solved this integration, and we got exactly the analytical prediction for R. So here only key is there, one writes on the mean field, okay? Find out the condition for the locked oscillator, and this interlayer term that we have approximated with the theta 2i, that is equal to minus, like theta 1i is equal to minus of theta 2i. And with that, we have solved this in the forward direction. And then one can see that it depends on this learning parameter alpha, okay? Gamma is nothing but this width of my distribution. So this critical coupling strength that depends upon alpha, which is the learning parameter. So as you can keep on increasing the alpha, the forward direction critical coupling strength that keeps on increasing. Now, again, I have to come back, and again, I have to start sharing. And now you can see that in the reverse direction, it doesn't depend upon alpha. So there is a two coupling strength. This is the forward direction coupling strength you can see, and there's a reverse direction coupling strength. As you keep on decreasing, you have this reverse direction coupling strength denoted by lambda b, and then this reverse direction coupling strength that does not depend upon alpha. So whatever alpha is there, only forward direction keep on increasing, reverse direction that does not depend upon alpha. With that, now let me try to summarize this portion of the talk, because I want to have a lot of things for discussions. That interlayer Hebning adaptation that triggers abrupt transition to synchronization of the interconnected layers. The emergent ES can be controlled through the Hebbian learning rule, and there's some limitation which I have not here focused. And these are some references for you all for the analytical and numerical simulations, which is most of the work has been done from these three. Most of the things which I have presented, the idea, this is from these three papers. And recently we have one very nice paper in archive where we have done the same thing, Hebbian plasticity learning, this kind of thing, but that is for the simplicial complexes. So instead of pairwise interaction, we have taken higher order interaction, which I don't want to tell here, but this is just for those who want to read and want to ask questions later. Feel free to read and send me mail later on also. Now, with that, now let me, I will try to give some other approaches also, but let me now further take some questions. So if there are any questions, please let me see. Yes. So there's one question. Everyone are asked to mark. Okay, I thought there is some question here. So now, so far I have told that this interlayer coupling strength was changing using Hebbian learning rule, but I can change this interlayer coupling strength. So the entire thing which I want to focus on here, that instead of intralayer, I'm changing interlayer. So now interlayer I can change using this order parameter. So far people have done this scheme where they have multiplied RA in the intralayer. What I have done, instead of intralayer, I have multiplied with the interlayer. And again, one can get the same kind of explosive jumps, which we have shown. And a lot of analytics, again, with the mean field kind of analytics. Again, we have to do the locked oscillator and try to solve this self-consistent equation in the continuum limit. And we have tried to show that how just by tuning this interlayer, one can get the transition to the synchronization, first order synchronization. And now let me now discuss something which is much more important, that this interlayer, like that was also a question from the audience, that why this particular kind of interlayer thing. And I want to actually initiate some discussion on this part, that of course we don't know the interlayer architecture, neither the coupling strength. For example, suppose if I give you some data of Facebook, you can very well can tell that who is connected with whom, and you can form an intra-layer connection strength and structure. I give you data for Twitter. who is following whom. Based on that, you can very well form the intralayer. But how activities in Facebook is affecting the activities in Twitter, that exact modeling of that thing is very difficult. In fact, in the brain, one knows that glial cells that interact in the regular fashion, and neural cells that largely interact in the random or scale-free fashion. And the activities of glial cell that affects the activities of neural cell, that also we know. But how? Sigma ZN, what is the architecture of Sigma ZN matrix and connection strength, that is unknown. And this is one attempt in that direction, that we try to evolve interlayer using some rules without fixing it from the beginning. And that is the gist of this entire efforts, that we don't want to fix this interlayer, and we keep it evolving with some kind of natural phenomena and something. So with that, let me now come to my final thank you slide, that it was all this work was possible because of my lab, complex system lab at IIT Indore, and a very good acknowledgement to the financial support from DST, CSR, and BRNS. And these are certain few external collaborators with whom I have collaborated or discussed about this work of multi-layer and the dynamical part. With this, let me thank you all for your kind attention. And if there is a further questions and discussion, I would like to take up those. Thank you so much.
Yeah. So, are there any questions?
Yeah. So the question delta omega means. So let me go to the slides. Okay. Do you know the slide number? Delta omega, which is just one second. Mean field analysis. Delta omega. Where have you seen delta omega?
Sorry, Dinesh, do you remember the slide number?
Where have you seen delta omega? Because I don't see delta omega here. But delta omega could also refer, actually, if you have seen, might be that mean frequency of the first layer minus the mean frequency of the second layer. So that also sometimes we refer to delta omega, that what is the difference between the mean frequency of both the layers. And any other question? Yes, okay. So when you mention heterogeneous network, okay, does it mean using a distribution for intrinsic parameter? Or okay, so here when I say heterogeneous network, this is the connection architecture of the network, not the frequency distribution. So heterogeneous network, for example, scale-free network is highly heterogeneous. So if both the layers are scale-free, then it's this scheme of interlayer adaptation that is not working. So frequency distribution, we are not imposing any restriction. The specific frequency distribution which I have presented here, that is because of the theoretical simplicity, because of the analytical calculation. Because if I have homogeneous frequency distribution or binomial kind of frequency distribution, Lorentzian frequency distribution, then it's easier to do solve that integration. Otherwise, you can take any frequency distribution which you want. And the second question by Prashant is that why it's called explosive synchronization. So no, first time it was referred as a first order synchronization. And later on, some of very nice writers, who keeps on coining the words, like Scholl coined the word of tweezer. So similarly, one very nice author or nice writer, he gave this word of explosive synchronization, and it became hit and very popular. So it is just explosive means sudden, maybe because of that, but technically it is the first order transition to synchronization, where the if you differentiate order parameter dr by d lambda, that is infinite, correct? So exact term is first order transition to synchronization. Explosive is just one of the popular term given by very nice writer. Now there's a further question that should hysteresis occur only while varying coupling strength, or why? Again, so the thing is that this transition, first order transition, there should some parameter which you fine tune. So what is the meaning of first order transition? You have a parameter which you fine tune, and the order parameter that shows a jump. So it's this kind of jumps. For example, now let me come back to the model and let me try to show you that what other parameters which can be in our hand. Okay. So suppose one parameter could be, for example, if we fix, suppose dii is fixed, okay, We are not evolving DII. And now one can try to plot this R1 as a function of DII also, whether it is showing the jump or not. Suppose lambda 1 is evolving with certain scheme, okay, and DII is acting as a parameter, not evolving with time, okay. Then one can try to see whether one is getting this explosive jump with DII also. That also is fine. But so far I have only focused that as you increasing the intra-layer coupling strength, okay, how this order parameter is changing as a function of lambda 1. But of course, you can change any other thing. And if order parameter of the system is showing a jump, that also is first order transition to synchronization. Yes. If that was your question. Yeah.
Yeah. Maybe some of you can unmute and ask.
Yes, please unmute or ask or write. If omega is constant for all, there is an, okay, so let me now try to address this thing. So suppose if omega, let us not talk about any second term and third term, okay. Now suppose we have omega 1 I, okay, and if it is constant, omega I is constant, but different for each oscillator, correct? So depending upon initial frequency, correct? Your all oscillator, so none of them would be synchronized depending upon the initial condition, initial phase, okay. But they will be locked, of course. Locking would be there, but synchronization would not be there. So oscillators would be locked, but there won't be any synchronization, correct? In fact, they would be not locked unless they have the same frequency. Okay, so let me now try to address. Suppose you take two oscillators, okay, and both have the same frequency, okay, but different initial condition. What will happen? They will keep on moving in a different position, but they will be locked because they will keep maintaining the same difference, okay. So those will be locked. But the oscillator, if they have the different frequency and even the same initial condition, after a certain time, they will keep on moving arbitrarily without any correlation between them. So answer to your question, for constant frequency, if each oscillator has different frequency, even the same initial condition, there won't be any relation between them. And that relation is arriving because of you have the interaction which is inducing between the oscillators, okay. So reverse of first graph of first order synchronization would come if we reduce R, or it would be different. So now answer to your question is this reverse direction what we are doing. So you can see all these plots. As we keep on decreasing lambda, R is decreasing, of course, as you also predicted, that R will keep on decreasing, okay? But it will not follow the same route as in the forward direction. So if you keep on decreasing R, lambda very small, adiabatically, it means very small step of lambda, then you can see that you get this hysteresis. It doesn't follow the same route, okay? So you can see there are two stable regime here. So for the nonlinear dynamics, this is a bistable thing. So you have this kind of bifurcation here, which is appearing here, you know. This is pitchfork bifurcation. So you can see that you have two stable state here. One is R is equal to 0 and one is R is equal to approximately equal to 1. So two stable state accompanied with one unstable state, which is not plotted here, that comes as you're decreasing lambda in the reverse direction. So it would be different here. Your answer to your question, yes, it would be different. The route to desynchronization would be different than route to the forward direction synchronization. That the synchronization plot is reversible or irreversible? No, it's not reversible. You can see it is completely irreversible. So you have in the this direction, you have a different route to desynchronization. So synchronization and desynchronization routes, they are different. And I have, I think, one slide for bistability diagrams. So let me try to show you if I have some bistability diagram after this one. And I think I had one. Yes. If this slide, if you all can see, this is for one Synchrometer oscillator with certain scheme. This shows the explosive synchronization, and this is from this Vocality's paper, scientific reports paper. This is there, and there you can see that you have this bistability. So R is having this. So finally, when you solve R, that is R is equal to root over 1 minus 1 upon KR, where K is here from this coupling term. And this is also plotted for homogeneous distribution. So one can see that you have two stable regimes. So this solid lines are stable, and this dotted line, that is for unstable. So this R has different roots. So if you plot this equation, you'll find the several branches, and two are stable branch and one is the unstable branch, which you can see here. And that exists in only the small coupling strength regime. So in this coupling strength regime, only one stable branch exists, which is R is equal to 0. Here in this coupling strength regime, ideally only one stable branch that exists. But here in this coupling strength regime, we have two stable branch and one unstable branch. And so this bistability is the essence of this first order transition to synchronization. Yes, or is there any other question? No, I cannot see any further question here in chat box. So if someone wants, can mute and ask the question.
Ma'am,
Yes.
ma'am, in single layer network, we only have one order parameter which tells us the state of this layer.
Yes, you're right.
But in the multi-layer network, we have, say, for instance, say 2-layer, we have two order parameter R1 and R2.
Yes, you're right.
Yes. Is there any possibilities that while considering only R1, the system, the layer exhibits first order transition, and while considering only R2, the system exhibits second order transition?
Yes, okay. That's a very good question. So I'm trying to see theoretically, because that if one layer is showing explosive sudden jump, okay, and
Yes,
second
ma'am.
layer does not show jump, and that's I don't think that kind of situation would be stable. So only one layer is showing jump and second layer is no. So one thing is maybe possible, which I know, that one layer is showing the jump and second layer does not show any jump but does not show the synchronization, also remains incoherent. Okay, but if one layer is showing jump, another layer is showing simple increase, smooth increase, I don't think this kind of scenario would be stable, because what will happen that suppose one layer has shown the jump, it means all theta 1 I are getting synchronized, correct? But theta 2 is still distributed. Okay, so that will I don't think that will be a stable state, because that will try to distort this synchronization in theta 1 I. You can see now that this term here is there, which is a multiplexing term. Theta 1 is all synchronized, but theta 2 is not synchronized. So that will be still like a noise for this theta 1. So I don't think that kind of state would be stable. And I have seen the kind of scenario where this state, the second layer remains inhomogeneous, okay, incoherent, okay, and first layer showed explosive jump. That can be still theoretically can be stable state. But one layer is smooth second order and one layer is smooth jump. I don't think I have seen, and that is possible to exist. But maybe, why not? Maybe one can find that kind of scenario, or numerically one can observe and try to see that theoretically. That, but I don't know right now. I have never seen, and I don't know that if it can exist and under what scenario it should be existing. What should be the criteria in order to have that one layer first order, one layer second order? No, I don't think it's possible, and I cannot think of any situation where it could be possible.
Okay.
Okay, now there's another question. Are there any necessary condition for explosive synchronization to occur in any coupled system? So this is a very good question. And the thing is that as I was trying to explain, that if you have some kind of frustration in the system, okay, so you know how the second order transition to synchronization happens, that you keep on increasing lambda, okay, and you have nodes which are satisfying this condition, which let me get back to this slide, that nodes which are satisfying this condition. So those nodes which are very close to the mean frequency, okay, they start coming closer. Okay, so you have the formation of giant cluster. So more and more nodes, as lambda is increasing, more and more nodes satisfying this condition. So this is omega I minus capital omega is the mean frequency. And as lambda is increasing, more and more nodes start following this condition and keep on contributing into R. It's a feedback kind of loop. So when lambda is very small number of nodes are satisfying the condition and contributing into R remains smaller. As lambda is increasing, more and more nodes are satisfying this condition and R is keep on increasing. So more and more nodes are joining the giant cluster. Okay. So now if we induce some kind of frustration in the system, which destroys the formation of this giant cluster. So nodes, as you keep on increasing lambda, still you have a small cluster. You don't have formation of giant cluster. And as lambda, which is the supportive field, so lambda supports synchronization, and this multiplexing, that is some kind of inducing frustration. But as lambda becomes very strong, suddenly it overcomes this frustration. So now condition which you are asking, that what is the condition for observing explosive synchronization, is that there should be some kind of frustration in the system, okay? But frustration should not be very strong. It should be some frustration, and the supportive field, which is lambda, if it can overcome this frustration, then you will get this kind of explosive synchronization. So you should have some kind of field which keeps on suppressing this formation of giant cluster. Then you would get, now this is a more qualitative kind of question answer, but mathematically I can tell you few schemes which can lead you, definitely it will lead to the explosive synchronization. And one scheme for multi-layer networks, which is very easy, is that if I take mean frequency of the first layer, if that is equal to the mean frequency, if that is very different from the mean frequency of the second layer. So suppose now first layer oscillators are homogeneously distributed, Gaussian distributed, with mean frequency suppose +5. Second layer also oscillators are Gaussian distributed, but mean frequency is -5. So now you can see the mirror nodes have the mean frequency which is quite apart, and that is somehow will play a kind of suppression role in order for the formation of the giant cluster. So one very mathematical scheme is that you take two layers, one layer, and that is also published. That is one paper by us itself in 2019 in Chaos. There we have shown that if you take mean frequency of one layer very different from the mean frequency of second layer, then you will get this kind of explosive synchronization. So that is one scheme. And the single layer, people try to achieve this thing by doing the degree frequency correlation. So what they do, the node which is having high degree, they make their frequency very high. And nodes which is having low frequency, they make their frequency very small. And if these two nodes are coupled, what will happen that since their frequency is that far apart, that will also suppress the formation of giant cluster. So this is one scheme that somehow you make the frequency of the connected oscillator quite far apart. So that will lead to the explosive synchronization. Another scheme is that introduce some kind of inhibitory coupling in the network. So suppose one layer you make inhibitory layer. That is also one of my student who is also here, Vasundhara. She has done very nice work in this direction, where what she has done, she has taken one layer inhibitory and one layer she has taken excitatory. And because of this inhibitory layer, this layer, inhibitory layer, does not show any synchronization, but because of this suppression, the first layer experiences some kind of frustration, and as lambda 1 keep on increasing, you get the explosive jump. So there are several schemes, and as I said that I have given some references there, you can get some relevant mathematical framework, mathematical model to get the explosive synchronization. But key is frustration. Okay, Gayatri, so I think if I have addressed your question correctly. So there is any other phenomena before, and after explosive synchronization? So if I understand your question correctly, explosive synchronization, you want to see if you had prediction of explosive synchronization, whether we have the system which shows something, but here you can see before explosive synchronization, it remains incoherent, you see, and there is sudden jump. So prediction of explosive synchronization, I think that is your question, and that is very interesting question, and this can be a good work for the people working on the machine learning kind of thing. Can you predict the explosive synchronization before its occurrence? Okay, sudden jump. Does system show some kind of correlation, which so far we don't have this kind of idea, but this is the open question, that before explosive synchronization, can you predict it? Does system show some kind of signature before it happens? And after explosive synchronization, no, it again keep on, you can see after explosive synchronization, sudden jump happens. If you keep on increasing it more, it is a very smooth increase or decrease. So after is not, but before it is a very $1 million kind of question, that can we predict this jump? And there is one paper I remember recently where they have tried to predict this critical coupling strength in the first order transition to synchronization, but I am not sure where is that paper and not the details of that one. But this is a good question, and good research work requires in this direction.
So, are there any other questions from the audience?
Ma'am, I have one question.
Yes, please. Sudarshan, yeah, please.
Ma'am, is it possible to have two different kinds of oscillator in two different layers and make a study on that?
So we have one paper, I guess, on dissimilar dynamics. That is in Journal of Computational Science. And there we have shown that we have taken two different oscillators. So one layer we have taken, so that is, let me show you which paper is that, maybe, but this again problem, I have to again share the slides, etc. But there's one paper which is explosive synchronization in dissimilar networks, that is in Journal of Computational Science in 2020. And there we have shown in one layer we have taken chromato oscillator, and second layer we have taken the chromato oscillator with inertia. And we have shown there that indeed we can achieve the explosive synchronization even in the dissimilar kind of dynamics also. So at least one work I know which is done by us. And I don't know, I cannot recall, but there maybe you have to do good literature survey, because it's a very hot area of research and a lot of papers which are appearing. So there may be, but at least as far as I know, I am not aware of any paper with a dissimilar, like suppose one layer Lorentz, one layer Rossler. No, I have not seen that kind of thing. But of course, this is not identical oscillators. These are not identical, but dissimilar, I know only one of my work. And that time, until that time, no one has done. So 2020, when we presented, we wrote that papers. That time, no one had done with the dissimilar one. After that, maybe if there's some papers, but you have to browse. And now there's a question by Gayatri again, that follow up to earlier question. Can we use statistical indicators, early warning signals? Yeah, that maybe I have not done work in that direction, Gayatri, but maybe one can try out early warning signals or something. I know one work where using machine learning, they have tried to predict that this critical coupling strength for the first order as well as for the second order. But I don't know if people have done and how it can be done. No, I don't know. Early warning signals or something, yeah, may be possible, but because it's extreme events, like you can think of that as like extreme events, but it is not, so you don't have, it just happens once. It's not like you don't have time series, long enough time series for multiple extreme events. So it happened just once, and I don't know whether your statistical indicators can do this thing without having multiple this kind of extreme events. So I don't know. That maybe some statistical mechanics person on those who are working on this kind of thing may try to do, because this would be very interesting if one can try to, because if you see the time series of chromato oscillators, I find there is actually no correlation which is there before the onset of before this explosive jump. So we were trying that if there's some correlation. Actually, there was no correlation, because one can see it remains into the completely in this incoherent resonance. So we have not observed that kind of thing, but maybe possible with other statistical mechanics technique.
Are there more questions? So I'm not seeing questions from audience. So if not,
Ma'am?
Yes, Preeti.
Ma'am, there should be a very small separation between the layers to get a good synchronization, or it can be any distance and you just need some kind of coupling.
Actually, no. So there are two questions. So one is, you require enough separation. No, if you suppress a lot, suppose if you put everyone inhibitory coupling, then entire synchronization will get suppressed. You require some small suppression, and then this lambda, which is the positive coupling, it should be able to overcome this suppression. Then only you will get this explosive synchronization. So if you suppress the dynamics too much, then I don't think that there should be some balance. The small frustration, and lambda should be able to overcome that frustration. Then only you should be able to get. What was your second part of your question? Or it was all?
If the separation between those two layers is very long, so we can't get
Long. What do you mean by separation very long? You're talking in terms of time. So here, this is the steady state thing. So with time, I am not changing anything. Your DAII is self-evolving. So what do you mean by separation? It's not like that we are putting some inhibitory force and we are removing. No. Whatever is there, it's a self-sufficient autonomous system. So we are not putting anything and removing. Okay. So I don't know what do you mean by long, because we are not putting anything with time and removing. It's everything is there. So one can talk about whether strength is large enough or not. Okay. And then, as I said, that if strength is too large, then maybe your lambda is not able to overcome that frustration. So you may keep on witnessing only incoherent state.
Okay, ma'am. Thank you, ma'am.
Are there any more questions? Okay. So if not, let's conclude the session. So let us thank Professor Saryachalan for giving a very illuminating talk on one of the contemporary works going on in complex network theory. So thank you, madam. Thank you very much.
Thank you. It was very nice. Only challenge today I faced that I don't know why it happened that slides was not moving so smoothly. So maybe I switched to Chrome, maybe because of that. So, but it was very nice discussing with you all. Thank you.
Yeah, anyhow, we are able to follow. Okay, thank you. Thank you, one and all.
Thank you. So I am now leaving now. Thanks.
Yeah, yes.
Thanks.
Bye.